So we're going to change pace a little bit today. Go ahead and click them all the way close. We're gonna talk about, I think the fun stuff for me, we're gonna talk about some applications of derivatives here. We're gonna focus on, excuse me, focus on derivatives as rates. And so this leads us into some physics. Let's start off, I'm just gonna throw you an example here. So what if we had something like, let's say we're gonna take the volume of a sphere, something like V. See if you remember that. What is volume of a sphere? It's been a while, hasn't it?
2 pi r's.
4/3 pi r cubed. There we go. So 4/3 pi r cubed is volume of a sphere. What if I asked you to do something in calculus? What if I asked you to do this? What if I wanted you to find V prime of r, which I could also write as dV dr. That's a derivative, right? Can anybody describe that as a rate? And I don't care about the answer here. Yeah, I know you guys can do the power rule. I mean, we could do that if we wanted to. So what is it going to be, I guess? Let's go ahead and take the good practice. What is the derivative? So what's the derivative of r cubed? Everybody? 3r squared. So if I bring the 3 down, 3 times 4/3 is 4. So 4 pi r squared is the answer. Agreed. But that's not what I'm asking about. What I want to know is how could you describe that? What would you say that is as a rate? How would you even say that? We know what it means. It's a derivative. It's v prime of r. But if I wanted you to describe that not as v prime, but as a rate, how would you even say that? The rate of what? How would you say that? We haven't really talked about derivatives in that way. We practice doing them, right? So here's how that would work. If we want to describe a derivative as a rate, we would always say it in this way. And let's make sure we understand why we're saying it in this way. We would say, literally, the rate of change of blank with respect to blank. You fill in the blank. What is this going to be? The rate of change of volume with respect to r. With respect to r, which stands for radius. Okay? And so don't lose sight of the fact. I mean, it's one of the, and I get in math, we kind of switch between modes. You know, a lot of times we're in, you might say we're in calculus mode or algebra mode, where we're focused on sort of the nuts and bolts of doing the calculus, because it's hard to do sometimes, right? But it's good to pull back every once in a while and kind of orient ourselves and say, you know, what does this really mean? Like, this is an actual function. This is an actual function that has meaning to us. It's a volume function, right? And so if I want to know what's the rate of change of volume with respect to radius, what is the implication now? What is that saying? I mean, that might have a real bearing on our lives if we're trying to inflate a balloon at a child's birthday party or something, right? Now, everyone's had this experience where when you go to blow up a balloon, it's pretty satisfying for the first few puffs, isn't it? Because it just shoots up, but then after a while, it's not so satisfying. After a while, what do you notice? As the balloon starts to get bigger, it's harder to blow up, and you don't see very much, you don't get much bang for your buck after a while. You're blowing on this thing, and it just doesn't seem to get much bigger after a while, right? Well, does this relate to that in some way? Yeah, kind of does, doesn't it? I mean, like if I pull up a graph on Desmos, if I pull up a graph of volume as a function of radius, there it is, right? There's volume as a function of radius. So this is not linear, is it? What's this telling you? As the radius increases at first, the volume's going up, not so rapidly, right? But after a while, as the radius increases, a small increase in radius means the volume is increasing pretty massively, right? So when you're first beginning to blow up that balloon, and the radius is very tiny, right? Putting in just a little bit of volume is pushing that radius out there quite a bit, isn't it? Right? But then after a while, adding some more volume, like if I'm going from, let's see, if I'm going from, I got it right here. So from here up to there, look, I'm only increasing my volume by a relatively small amount, but the radius is increasing by a really large amount, right? What about up here though? If I'm going from there to there, look, the volume is increasing a lot, but the radius now is barely even moving, right? So it takes really large increases in radius after a while to affect large increases in volume and vice versa, right? So then after a while, tiny little puffs of volume are going to barely move the size of that balloon, right? Okay, and so it really has an implication for us. But when we talk about these rates, they do give us something beyond just the static. If I have a certain volume and a certain radius, it's easy to attach those two things to each other. But calculus is dynamic. Calculus is about rates of change, right? And so if we look back at this picture, a derivative relates to what part of a graph? The slope, right? And so when we're looking at a rate of change, we're looking at, we can see that in the slopes of the tangent lines. Like right here, if I want to try a certain radius, let's say we're going to take a radius of 2, and I want to know what the rate of change is, well look, that's getting at the slope of that tangent line. The slope of the tangent line at 2 is going to be pretty dramatically different than it is down here when r is 1, okay? Does that make sense? Okay, so, not to belabor this too much, but I feel like it's worth it. What's the implication here? Talk to me more about this. I want to hear more from you about this. The rate of change of volume with respect to radius. Articulate, what's that mean? For a small change in radius, what's that telling me essentially? Okay, it's telling me what the corresponding change in volume is going to be, right? Probably the easiest connection to make, we're going to go back to kinematics, right? I think the easiest way to get at this is with kinematics because it's something we're so familiar with, right? And once again, how many people are in physics? Okay, so if you're in physics, you don't have to be in physics to appreciate this, but this really helps, I think, with the physics part of it too. They tie together so well. So let's look at this concept of derivatives as rates of change within the context of kinematics. So let's remind ourselves, it's been a little while since we talked about this at all. So if we're going to define something like, let's say, we'll call it x of t is our position function. That's our position function on a line. Can you define for me what the other kinematic quantities are? Right, so position, what would come next? Okay, so we got, what's the next one though down the list in kinematics? Got position and then what? Velocity. Okay, so we'll call it v of t equals velocity. And what's next? Acceleration. So a of t equals acceleration. What's the calculus relationship? Right, so we know, we talked earlier about how in your physics classes, you're talking about algebra-based, non-calculus-based physics. So when you talk about velocity, you're really talking about average velocity, right? But if we want to talk in calculus now, we have the ability to talk about instantaneous velocity. Do you remember what we said? What's the definition of velocity? Yeah, that's better. What's v of t in terms of x of t then? What's our calculus relationship?
It's x prime.
Okay. Right, velocity is the derivative of position. What's acceleration?
X double prime.
Okay, so the derivative of velocity, which is the second derivative of position, right? And maybe let's even take a second and let's kind of review. Let's just take a brief second. It's been a little while. That's probably good to do. Let's just review what the graph's going to look like. So I want you to remember this game. I want you to tell me if this is going to be the position function. So that's going to be x of t. Think about that for a second. I want to know what's a corresponding graph of a velocity function. So that would be the derivative of that graph. Okay. Redmond, what do you think? Now, let's remind ourselves first, though, before we jump into the graph, what's the velocity is the derivative of position. The derivative relates to what part of the function?
Slope.
The slope, okay. So what do you think? What's that going to do? Okay, so starting, he's going up an angle? Yeah. Okay. Something like that. Everybody agree? Does that make sense? Okay, good. How come? It's right. How could you convince somebody of that? What's going on with the, how does the blue function relate to the red one there?
It's increasing.
The,
The slope is increasing.
okay, the slope's increasing, so if I were to look at like little tangent lines, the slopes of the tangent lines are getting bigger and positive, right? They're starting at 0 and they're getting more positive. So that makes sense? All right, so Rem, what would be maybe the acceleration graph then? That's going to be the derivative of the red graph, right? So what can you tell me about the slope of the red graph?
It's increasing.
It is the slope?
It's,
is
no,
increasing?
it's constant.
Constant and positive or negative?
Positive.
Okay, so then what would the acceleration graph look like?
Like, no idea. Horizontal.
Just be straight.
There you go.
Yeah.
Like that?
Yeah.
Okay. Okay, right, makes sense?
Yeah.
Okay, one more. How about if we do, I'm gonna throw a tricky one at you, how about something like, do that. Let's see. First part. What do you think? Volunteers. What do you think? What's your- Okay, so negative slope line, starting from where? 0. Okay, so starting here, something like that for the first part. Would you agree?
Yeah.
Does that make sense?
Yeah.
Doesn't that, and how come, once again? We've got horizontal tangent lines, so 0 slope, the tangents are decreasing, right? You're getting increasingly negative, aren't they? Right?
Yeah.
Okay, good. So if this is x of t, then this would be v of t. Okay. What else? How about the acceleration? Emily, how about the acceleration? What's that going to look like? That's going to be the derivative of the red one.
Just be a
Straight
straight.
line, positive or negative? Negative, okay. I took that to mean a constant value. I knew what you were saying. Okay, good, so there's our acceleration. For the first part, now what about the second part? What about the second part there? the position, it changes pretty radically here at the end. And how would you characterize, what's the slope of that blue line, part two? If we kind of break, let's cut this thing into pieces. Constant and positive, okay, so then the red would look like this, something like that, okay? And then what would the green be?
0.
0, okay. Okay, what about the boundary between the two? What would I have to do there, Evan? What am I gonna have to do, so at this point right here, what's the derivative gonna be? Or is it gonna be? What do we, now, think back to our,
Because it's a corner.
okay, good. So what about corners? There's something going on there. Where are derivatives not defined? Sharp corners or discontinuities, right? Or asymptotes, or there's one other place that we don't see very often, that's where we have vertical tangent lines, right? So we'd have to, because that's a sharp corner, what do we have to do to the red derivative function there? How do we indicate that it's undefined at that point? Open circles, okay, good, something like that. And then, do you see here, this is kind of interesting. From that point forward, every successive derivative is going to inherit those discontinuities, right? Because if the function's discontinuous, then the derivative necessarily is, right? What do we say?
Discontinuity, or no?
What do we say?
What is that?
What's the relationship between differentiability and continuity?
Differentiability implies.
Differentiability implies continuity.
That's
There you go.
That's almost-
There, that's what we're looking for. I can see you're working with that. Okay, so good. Now let's move forward here. Let's look at some interesting examples. I want to get to one today because one of them, there's really some cool stuff you can do with this. And this is more physics than it is calculus, but I want you to see that the two are related here. They're related by the fact that the kinematic quantities are connected by calculus. So suppose the position of an object moving horizontally after t seconds is given by this position function up here, right? So we're saying s is position, and we're gonna look in this domain where t is pinched between 0 and 8 seconds. Okay, so that's a model over that time period. Where s is measured in feet, find the other kinematic functions first of all. Well, that's just calculus. So if this is the position function, then what's the what's going to be the velocity function? That's just, we just have to differentiate that. So if that's s of t, what's v of t going to be? Somebody help her out. What are we going to get for?
24 minus 8.
And that's all we're doing, is just taking using the power rule, right? So the derivative of 24t would just be 24, and the derivative of 4t squared would be 8t. There you go. So that's all we're looking for there. What about the acceleration then? Yeah, derivative of a constant is 0. Good. So we'd end up with just a negative 8, right?
Yes.
Okay. So there's our kinematic quantities. Now, what if we want to determine the velocity and acceleration of the object after 1 second? So we're just going to be able to use these kinematic quantities that we've obtained through calculus. But before we do that, let's kind of remind ourselves what one-dimensional kinematics looks like, right? So if this is, we're going to talk about motion on a line at the front of the room. We're going to define this, how about as the starting point? So this is going to be my 0 point, right? So then I would say that if this is position 0, this is position 1, that's position 2, etc., right? So then, what would this position be, presumably? Negative 1. So position can be positive and negative. It's a vector quantity, right? What about velocity? Describe, if I'm covering 1 meter every second as I'm walking up here, describe this velocity. Okay, describe this velocity. Okay, negative 1 meter per second. How come? Okay, because it's in the negative direction. Okay, good. So what about acceleration? Now, what if I'm starting from rest and I'm going to do something like this and I'm going to pick up speed? Is that positive or negative acceleration? Positive. Positive. Okay, good. Now I'm trying to trick you. What if I start here and I'm at rest, and I'm picking up speed now in this direction.
Positive.
Once again, do that again. I'm starting from rest here, and we start walking, and before you know it, I'm sprinting, picking up speed in that direction. It's negative. Negative. How come? Okay, now this is, it has to do with the fact that it's acceleration is the rate of change of velocity, right? In what direction is the velocity changing? Is it going from positive to negative or negative to positive? If my velocity is becoming more negative or more positive? More negative, right? So it's going to be, the rate of change of velocity then is a negative quantity. This is where the invisible hand helps, right? If you're in physics, you know that acceleration is related to force, right? But ignoring that, if you think about an invisible hand as being the cause of the acceleration, all you ever have to ask yourself, this is a great trick in physics, all you ever have to ask yourself is the invisible hand pushing me in the positive or negative direction, right? Well, clearly, if I'm starting from rest here, and I'm picking up speed in that direction, the invisible hand is pushing me in which direction? Negative, right? Okay. Now apply that to something a little trickier. What if I'm moving along here at constant speed and I start to slow down towards zero? Positive or negative acceleration? How come? You're right. The invisible hand was pushing me in that direction, right? Make sense? So it had to be negative acceleration. What if I'm trucking along at a pretty good rate here and I'm slowing down to zero? Positive, right? How come? The invisible hand was pushing me in the positive direction. Okay, so it's helpful to use that kind of a cue when you're thinking about positive and negative accelerations especially. Okay, so now let's look at this problem. It says determine the velocity and acceleration of the object at t equals 1 second. Well, how would I do that? That's no big deal. Plug in 1 into the appropriate function, right? So for this part, all I've got to do having some real difficulties today. All right, this is okay. So at 1 second, if I want to determine the velocity, well, that's just v of 1, which is what? 16. And then what, about feet per second, I guess, if we want to attach units. And the acceleration,
Negative 8.
it's always negative 8. It's constant, isn't it?
Yes, sir.
What would the units of acceleration be?
Feet per second squared.
Okay, feet per second or feet per second squared. Not that we need to get hung up on the units, not a big deal. Okay. How about this? Determine the position and acceleration of the object when its velocity is 0. Determine the position and acceleration of the object when its velocity is 0. What am I going to do there?
There's some velocity. So
Minus
zero.
0.
Okay, so I'm going to set the velocity equal to 0.
Yeah.
So that's how we petition the math gods for that information. We just set up an equation, right? So the velocity functions up here, I'm going to set v equal to 0. I just get 24 minus 8t equals 0. Push the 8t over here. So what's the solution? T equals 3 seconds is when that happens. And so what would I do to find the position and acceleration when the velocity is 0? Okay, so that tells us something important. Whenever we talk about a when in physics, right, we're talking about a particular instant. It's helpful to think about this, remember, as when we're looking at an action like this, or me walking along the front of the room, it's like it's on a camcorder, it's a video, and each frame in the video corresponds to a moment in time. So we want the frame corresponding to t equals 3. Once we know what the time is, what frame we're looking at, then we can go back to our kinematic quantities, and notice they're all indexed by t, right? They're all specific functions of the input variable t, and so we can go back and plug in any time that we want to and figure out what the values of those quantities are. So that's no big deal. We can just plug a 3 in and come up with some numbers. Okay, what about this one? When is the object moving right or left?
Anytime after it's moving left.
Okay,
Anytime.
how come? What do you, you're right, but how come?
Because the acceleration's negative, so then anytime past 3 would be moving, so.
Okay, so if the object is moving right or left, which kinematic quantity are we interested in there? What's telling us if the object's moving right or left? Velocity, okay? Moving to the right means what about the velocity? Positive. Moving left means negative. And so all we'd have to do then, right, if I wanted to figure out when the object is moving to the right, is I would just have to ask the question, when is my velocity what? Positive. How do I say that mathematically? Greater than 0. Okay, if I want to figure out when it's moving to the left, I would just ask the question, when is my velocity less than 0, right? And what is the velocity? Well, we defined that when we took our derivative. It's right there, okay? 24 minus 8t. So we could solve those and come up with those, and that's, what are we going to end up with in our answer? T, right? Let's do one of these. What if I solve this inequality? How could I solve this one? What am I going to do? You'd walk me through a bunch of ways I could do it. Add 8t to both sides, that's fine, so I get 24 is greater than 8t, divide by 8. And so I end up with what? T is less than 3. So for any amount of time less than 3, we're going to be moving to the right. Well, when must we be moving to the left then? Greater than 3. Now, our domain is limited to be between 0 and 8. So what that would imply is that we're moving to the right when t is greater than or equal to 0. And do I include 3? Nope. Just less than 3. Okay? On what intervals is the speed increasing? What about that one? That's a little tricky. That's a little tricky. Now, is speed the same as velocity? Okay, what would we say speed was? Here we go back. Okay, so velocity has directionality. Can speed be negative? No. No, speed is just the magnitude, right? Independent of direction. Okay. So how could we come up with something like that? It's, when is the speed increasing?
It's anytime above 6 seconds.
Anytime, how are you getting that?
Because you just plug it, you solve for that when it ends up being above 24 for speed. Because you're trying to find when their velocity is above 24. Which is
Why above 24?
Because that's what it is with 0. So that's like the initial speed is 24 at 0, and then you're trying to find when it's above that, when your velocity is above 24.
Okay. So how does,
So because at 6, it would be equal to 24 again.
how about if we graph, what might be helpful to do here, and there's a bunch of ways we could approach this. What if we were to graph the velocity function? Would that be helpful maybe? Okay, so if we graph v is 24 minus 8t, we don't need any fancy Desmos to do that. We can do that stuff, right? So if we were to graph velocity, so we're going to have velocity on this axis and time on this axis. What does that line look like, 24 minus 8t? Negative slope, and what's the y-intercept? 24, or the v-intercept, I guess. So it's going to do something like that, right? Yeah. Agreed? So if that's the velocity, it's starting at some positive value, and then it's decreasing down to some point where it's 0, right? And we figured out that was 3 seconds, wasn't it? We did. Okay, and then it just keeps, then it gets negative and more negative, right? Okay, so is the speed increasing between 0 and 3?
Yeah.
It is?
No, it's speed.
It is. If
Accelerating
we're
slower.
starting with some positive velocity, and now it's a smaller positive velocity and smaller positive velocity, and now it's zero, that sounds like slowing down to me, doesn't it? Right? So we started off with some pretty high velocity, and I'm just slowing down. I'm moving in the positive direction, but I'm slowing down. In what direction is the invisible hand pushing me? Hold on. If I'm
On the
starting
right.
off with
Slowing
a
down.
large positive velocity, so I'm running in the positive direction, here's me running. And then 3 seconds later, I'm slowing down. 3 seconds later, my velocity is zero.
You can slow it down.
In what direction was the invisible hand?
From the right.
pushing? Okay, to the right. Doesn't that make, look at the acceleration. Negative. To the right, isn't it? Pushing in that direction. Okay, then what happens? Then from here, my velocity, it was zero, now it's gonna start to get negative. First it's small and negative, but it's getting bigger and negative, so at this point, I'm picking up speed in this direction, right? So where is my speed's decreasing for the first 3 seconds, isn't it?
Yeah,
But then I'm at rest, and from that point forward, what happens?
it's increasing.
It's increasing. Now, my velocity is getting negative, but speed doesn't care, right? Speed doesn't matter about it. Directionality makes no difference. It doesn't have a sign. Just how fast am I moving? Well, I'm moving increasingly fast in the negative direction. And so this one would be, where does the speed increase? For the values of time greater than 3 seconds, right? So between 3 and 8. Well, that's kind of a tricky one. All right, here's the one I wanted to get to. This is a good problem. So it's really amazing that we can do this. So El Capitan in Yosemite, that's that big. You guys, how many have been to Yosemite? It's an amazing peak. It's about 3,000 feet above the valley floor. So here's the experiment we're going to do. It's about 1,000 meters up off the floor. If we were to shoot a bullet straight up in the air from the top of El Capitan, the question is, how high is it going to go? How long does it take to get to that point? And let's ask, how long does it take to reach the valley below? So what's going to happen is we're going to shoot this gun straight up, this rifle. Bullet's going to go way up in the air. It's going to come down right by us and continue right down the face and hit the valley below. Okay. The bullet is going to be coated with sliprium, which is extremely expensive stuff. It's completely eliminates any friction with the air. Okay. You get it at the Acme store. It's, like I say, very expensive, hard to find, but it's available there. And the muzzle velocity is 1,000 meters per second. I'm going to tell you what the position function of the bullet is. That's it right there. Okay, so we're going to use y for our position function this time because it's vertical, right? So y is vertical. So y of t equals 1,000 t minus 4.9 t squared plus 1,000. So how could we figure out how long it takes the bullet to reach its highest point? Say it again. Okay, so I mean, we could use it. We could probably solve this quadratic function and find its peak, but that doesn't sound like a lot of fun, right? And it's a polynomial. And what do we say about polynomials? The derivatives get successively easier when we differentiate polynomials. So if we calculate the velocity function, what's our velocity function doing? It's an easy one, right?
Yeah.
What's the velocity function?
1,000
Minus
minus
9.8 t, that's it, right?
Yeah.
Okay? And so all we'd have to do is now that's pretty easy to solve. We just want to figure out, it's going to get to its highest point when the velocity reaches 0, agreed?
Yeah.
Okay? So we could just set that equal to 0. Right, so if I add the 9.8 t to that side and divide by 9.8, everybody agree I'm just going to get t equals 1,000 divided by 9.8?
Yeah.
What is that? Just a little more than 100?
Mm-hmm.
102, about?
Yeah.
Okay. So about 102 seconds it takes, okay? How long does it take? 102 seconds. How high does it go? How could we figure that out?
You put the second in position.
Okay, there's my position function, right? So now what do we do? When we establish that the time is 102 seconds, we pick the frame in the movie. It's that frame. It's the frame where it's, at 102 seconds. Now our movie, you know how these movies now, they have like different views? You can do the cinematic view, you can do, well, we have our three views are gonna be the position view, the velocity view, the acceleration view, right? So if we wanna go to the position view and we plug in 100 seconds, I'm gonna get some value. What do we get? If I plug 102 in for t into y. So y of 102 equals 1,000 times 102 minus 4.9 times 102 squared plus 1,000. What's that give us? 52,020? Okay. So that's about 10 miles, okay, theoretically. Is it really gonna go that high? No. I mean, the air resistance is gonna have a, but we got our slip.
We got
index,
slip
right?
index.
So maybe we're chilling. So it goes up about 10 miles. How long does it take the bullet to reach the floor of Yosemite Valley? Ooh,
That's a good question.
yeah. How am I gonna figure that one out?
You want the acceleration.
We could calculate acceleration. It's gonna be pretty boring. If I calculate the acceleration by differentiating velocity,
Do we just take the,
what is it?
Negative 9.8.
-9.8, and it's constant, right? It's not ever gonna change. How long does it take the bullet to reach the floor of Yosemite Valley? So when is that happening?
when it's 1,000 meters?
So now notice that the position function, by the way, is measured relative to the valley floor.
Yes.
Okay?
So we need to take that out.
So if the position function is measured from the valley floor, and I can prove it to you, because if I plug 0 in for t, what do I get for my position function? Is everybody, I feel like not everybody's getting all this. Everybody focused on this? Everybody got this? If I plug 0 in for t, what's gonna happen to this function?
You're gonna get 1,000.
1,000, which is right, because it's 1,000 feet
So you
above,
just need to-
that's L cap, right, 1,000 meters up.
Yeah.
So how long does it take to reach the floor of Yosemite Valley? Which one of those kinematic quantities is gonna be the one that's important if we know that the height,
Position.
the position is 0, right?
Yeah.
Everybody agree? So I've got to set the position equal to 0 and solve. Unfortunately, that is a quadratic function, but that's all right. We can use technology to do it. We're just solving the equation 0 equals 1,000t minus 4.9t squared plus 1,000. Well, let's let Desmos do the work for us. Right, so in Desmos, all we got to do in Desmos is when we want to solve an equation, why does it do this? I have such problems with it. There we go. Okay, so if we want to set, we're going to solve that equation right there, right?
Yeah.
Remember, we got a great trick. When we're solving, we're numerically solving using technology. We're just going to set y equal to the left and y equal to the right. So I've got y equals 0. Well, that's just, that's just the x-axis. And then I'm going to have y equals 1,000 t minus 4.9 t squared plus 1,000, and then I just need to zoom out and find all the places where that intersects 0, right? If I zoom way out, there's 2 of them.
Yeah.
Okay, well, one of them, that's probably the one that you think we want right there, isn't it?
Yeah.
About 205.077. Okay. All right, hold that thought. Hold that thought. There's something really cool is coming out of this, I promise you.